All right, welcome back. This is part 2, lecture number 6. We're going to move beyond linear optimization. So we've talked about linear optimization. All that means is that your objective function and your constraints are linear functions of the decision variables. Okay, and there's several special subclasses we examined, including network optimizations, integer optimizations, and binary optimizations. So now we're going to move beyond that and kind of broaden the horizon and consider more kinds of problems. So first we're going to talk about nonlinear optimization, and then with whatever time we have left, we'll briefly address non-smooth optimization, which is yet a broader class of problems that can be solved. So let's talk about nonlinear optimization. So where linear optimization, like I said, requires linear functions, a nonlinear optimizer can solve for nonlinear objectives and or nonlinear constraints. So we can use nonlinear functions like square root or square or cubes or logarithms or anything like that. Okay, so we can start using any kind of function as long as it's smooth. That is, as long as the first derivative doesn't change abruptly, as long as there's no breaks in the graph or sudden sharp turns. Okay, so as long as it's a smooth graph, like all those things I mentioned are, so square roots or squared values or anything like that, they're very smooth. They're not linear, but they're smooth in their appearance. Then we can use a nonlinear optimizer to solve them. The trade-off is, so we can solve more problems, more classes of functions with a nonlinear optimizer. The trade-off is we won't be guaranteed to find the globally optimal solution. So we're not actually guaranteed we're going to find the best solution after all. We are at least going to find what's called a local optimum solution, which means it's better than any of the close or similar solutions that you can think of. Okay, so there's no other solution like the one found which is better, but there may be a solution that's very different that's even better. Okay, so we will find a local optimum better than similar solutions, but not a global optimum that's better than all possible solutions. That's going to be our trade-off. So just to examine why that is, let's take a look at this graph. So this is just a simple y versus x graph. Simple function, simple function of one variable, but obviously a complex function in that it has lots of curves and turns and things. It's smooth, so all those points are very smooth. This first derivative is smooth. However, you could ask the question, what's the maximum value achievable by this function? Now, for you and I, it's pretty obvious that the maximum value occurs up here, right? It's pretty easy to see. The problem with a nonlinear optimizer is the way nonlinear optimization works, because it doesn't have a view of all possible solutions and what value the objective will have for it. All it knows is if I'm at a certain point, say right here, and I found a solution that gives me this objective value, if this blue line is the objective that I want to maximize, then the nonlinear optimizer can either choose a solution that's like that one but to the left, so something with a lower x value, or it could choose something to the right of that with a higher x value. And what it knows is nearby solutions seem to go up if I go higher x values. That is, if I go to the right, say over here, then I'll get a better objective. And furthermore, if I go right again, I get even a better objective. And it keeps moving step by step in the direction of a better objective, one by one. Okay? And eventually, it will climb and find all the way at the top here that it can find a solution with this objective value for which no solution to either side, either a higher x or a lower x, seems to be any better. Okay? However, let's imagine that the solution or the optimizer started over here, in which case it would find that a lower x value gets a better objective, and an even lower x value, and so forth, and it would move step by step, okay, till it found that there was an optimal y value for some x here, say about 0.35, for which no nearby x value is any better. In which case it's found this point, which is a local optimum. Okay? It's better than the points around it, but not necessarily better than every point on the graph. And the reason why the nonlinear optimizer works this way is because this is a fairly smooth and simple function. Imagine you have a function of 10 variables that's curved and bending in all sorts of directions. To find a good solution, the best the optimizer can do is just take tiny steps, one by one, toward better and better solutions that have a either higher or lower objective value, depending on if you want to maximize or minimize. Okay? It can't get a global view like we can of this function and identify the best value. The best it can do is pick a starting point and then move step by step in the direction of better solutions. Okay, this approach. So that's just what I said. This procedure. So we start from a current solution and we consider the nearby or the close solutions. So in this case, an x value that's either a slightly bigger or slightly smaller than the x value of the current solution. And we choose the one that's better, and then we repeat. From there, we move one direction or another, and so on. Okay. Sorry, that fell off the screen a little bit. This approach is called the hill climber or gradient descent approaches. You can imagine if you're trying to climb to the top of the hill and you start somewhere here, you just start moving in the direction of the hill going up until you find the top of the hill. Okay. That's what this nonlinear optimizer does. So it has a starting point and it just moves up the hill, assuming you want to maximize. Or if you're trying to minimize, it moves down the hills, right? It descends down the hill. So hill climbing or gradient descent are common terms used for this kind of a problem or this kind of an algorithm. The Analytics Solver platform names its algorithm the Large-Scale Generalized Reduced Gradient, so LSGRG, and I'll show you that in Excel in just a minute. So that's how we can identify that it's using the algorithm suited for nonlinear optimization. Okay, and again, nonlinear optimization can only guarantee to find a locally optimal value. Now, I say that it may not technically find the true local optimum, because what it may find is it has to take such tiny steps back and forth trying to find the true hill peak, let's say in this case, that eventually it stops after using so much time and just tells you the best it got so far. So it may actually get very close to a local optimum, but not quite there. And that's all that a nonlinear optimizer can do for us. Okay. Now, what we want to do, ideally, is try to pick some various starting places for the algorithm to start from and run the optimizing algorithm, the optimizer algorithm, from each of those starting places and see which one found the best solution. Ideally, if you picked enough starting places, eventually you'd pick one that would lead you to find the global optimum. Right? Eventually you'd get to the highest hill if you picked enough places to start from. Obviously, the problem is you may never know if you found that highest hill. You may never know if you've picked enough starting places. Okay, so that's the trade-off. So more expressive in that nonlinear optimization can handle more kinds of functions, but less guarantee of the solution it finds. Okay, let's take a look at a few examples. So in this case, we have a paper company. It has 10 cities that it ships its paper product to, and it's trying to decide where to locate a distribution center. Subject to the objective here is to minimize the total sum of the distances between the distribution center and each city. So there's 10 cities, and we're going to represent them here by just XY coordinates. You could think of those as longitude and latitude or something like that. And we just want to pick an XY pair, not out of these options, but any XY such that the distance between that chosen xy location for the distribution center minimizes the distance to all 10 of these sites. So the sum of all those distances. Okay? So that's the solution, or that's the problem we want to solve. So jump into Excel. I've actually already put all the data in. So we have all 10 sites, their x and y location. And what we want to do, so here what we're going to decide on is an x and a y pair for the distribution center. So let's just pick an initial set of values, say 0 and 0. Okay. Actually, I'm going to move those down here. There we go. And as I always do, I'll mark those orange for being decision variables. Okay. So this is the distribution center x and y locations. So what we want to do is compute what's the distance between this pair of coordinates and each of these 10 pair of coordinates. Okay. Now, if you assume if this is a two-dimensional world that we're working in here, we can use Euclidean distance and just say if you took the the difference between the x values squared added to the the difference of y values squared and the square root of all that, that's the straight line distance. So it's the distance between this pair of coordinates and this one. So I'm going to compute that. Okay. So distance here is this x value, I'm going to do square root of this x value minus the distribution center x value. I'm going to make that an absolute reference. Okay. And I'm going to square that difference. Okay. Adding to that the difference between this site's y value and the distribution center y value. Again, I'm going to make that an absolute reference and square that value. Okay? And then I'm going to take the square root of that sum. Okay? So simple Euclidean distance, basically trying to find, the straight line distance between 2 points in a two-dimensional space. So we'll make that our distance metric. So in this case, the distance between 0, 0 and 541 is a distance of about 41 units. Okay, a little more than 41 units. Okay, and because I used absolute references here, I can just copy this formula down, and the part of the formula that has to do with the site will change row by row, but the part of the formula that has to do with the distribution center will stay the same in each row. So now I have distances, okay, for each site. Okay. And now what I'll do is I'll just sum those up. So the sum of distances in this case. Okay. And that will be my objective. Oops. Okay. There we go. So by choosing different x and y locations for the distribution center, let's say if I chose, so 0, 0 gets me a sum of distances of about 1178. If I chose 10 and 10, my sum of distances went down to 1059. Okay, so we might keep moving up. That's an even better sum of distances and so forth. Obviously, though, there's two variables, and it's not necessarily clear if we should be increasing one or both, or decreasing one or both, or some combination of those, right? So what we want to do is use the nonlinear optimizer to solve this problem. Now, the reason this has to be nonlinear, obviously, is that our objective, the sum of distances, well, the distances involve squared values of our decision variables, and then the square root of the sum of those kinds of things. So it's obviously not a linear problem, right? The squares and square roots being involved of our decision variables makes this nonlinear, but it is smooth. Square functions and square root functions are smooth. So it's we would call it a nonlinear problem. So let's set it up. So the objective here, we're going to try, to minimize the sum of distances, and we're going to make these two variables the decision variables. In this case, do we have any constraints? Let me ask this. It appears as though all of our x and y values are positive. It might be reasonable to assume that the distribution center xy values should also have to be positive. Do I have to add a constraint to say that? So I see a few nods maybe of no. And that's right. I don't have to tell it that the decision variables have to be positive in this case, okay, because there's no way that negative values here would lead to lower distances to all of these positive values up here, okay? So if negative values are illegal, I don't know that they are, I'm just asking, but if we would say that negative x and negative y values are technically not valid, there's no point in us constraining the solver to say that, because that would be a bad solution irregardless. Okay, it would be a poor solution anyway. So the best solution should have to involve positive x and y values. Okay, there's no reason why it wouldn't. Okay, to get a lower distance. So we should be able to run the solver. Now I'm going to show you on the engine tab. So instead of letting it automatically select the engine, and instead of using the linear programming engine, we're going to use the LSGRG. That is the large-scale gradient or generalized reduced gradient engine. Okay, which just means that gradient reference there just means we're climbing or descending hills. That is, we're just trying to find locally optimal solutions to this very strangely shaped function. Okay, this objective of ours. So we're going to use that engine, and we can run. Apparently my license is run out within the last 20 minutes.
Sometimes it does that when you're formula around.
Okay. It may have had to do, I had multiple Excel windows open as well. So let's make sure I have entered everything correctly. B16 and C16, okay. Let's try rerunning. Alright. Let's just try restarting Eclipse, because we definitely saw, so that was that solution. So we'll restart Excel, see if that helps. Doesn't seem likely anyway that my license expired within the last 10 minutes. But if it were going to expire, the middle of class is probably the time it would do it. I think there's a law that states that. So let's try this again. Okay. Well. Well, this is how you would set the problem up. This is how you could run the algorithm. Let's take a break. Sorry for the interruption. Let's take a break. I'll see if I can get the licensing problem resolved. If not, will likely have an abbreviated class tonight, okay, which I'm sure makes you sad, but that's okay. You'll make it. We may go ahead and talk about more of the problems and how to set them up. I won't be able to demonstrate running the optimizer. But what you would expect to see is, obviously, it would choose values for x and y here to minimize this value here, right? And again, depending on the starting values you gave it, it could technically come up with a different solution. So if we started from 0, 0, it might find one solution. If we started from, say, 100, 100, it could technically find a better or worse, but different solution. So let's go ahead and take a break.